Hi there, my name is Jacob and today I'll be guiding you through a little whistle-stop tour of some cursed computing. This is a little different to what I'd usually do. I'm usually semi-serious in what I do here, but I thought I would take a slightly lighter approach to this talk, given that it is, amongst other things, my last talk here as an actual undergraduate student. So obviously I hope to do some more talks, but anyway. This is a short journey through some of the bits of cursed computing that I find interesting, particularly from the cursed computing iceberg, which you may have seen, and I'll show in a minute. So, let's start off by thinking about cursed, what we actually mean by that. I mean, people probably know what they mean by cursed and feel what they mean by cursed, but there's no real good definition for it. There's a few definitions. I mean, like the Wiktionary definition we've got here of under some defined harm or malady isn't really a good definition, really, but something you'd find very scary and possibly you'd become cursed just by seeing and so on. Maybe that's a bit closer. And something almost impractical or outright strange is probably closer indeed again. A lot of the time this is things like bugs or just unintuitive behaviour of computers, but it can't really be as solidly defined as that. So what do we mean by the iceberg when I mention the iceberg? Well, I'll show you it in a second, but as the creator described it, it's not a hall of shame. The intent is to awaken people to the many peculiarities and weirdnesses of computing, and hopefully, after having a look at them, you will learn something and embrace the chaos. So, I don't know, maybe we don't want that. Anyway, this is what the tip of the iceberg looks like at the very top, and we're going to be jumping around semi-randomly on some light themes, but I encourage people to go have a look at this. The link will be in the notes. So let's start on the abstract side of things, with computing with vision. We're not talking about computer vision here, we're talking about vision as computing. Specifically, we're thinking about, can you compute just by looking at something? And the answer, as it turns out, is yes. Yes, you can. So, some rather interesting work produced these interesting optical illusions, which, for instance, here you can see an OR gate implemented as an optical illusion. So when you stare at these, based on the state of the ones and zeros at the top, you'll see a 1 or 0 result. But how will you see it? Well, you'll see it as whether or not the angle appears to be to the left or to the right. And if you stare at the objects here, you can see that the angle of 0, 0 appears to be different to the angle of all the others. Though, caveat, you do kind of have to look at them a particular way for this to work. So these are the AND gates again. So you can see here that 0, 0, 1, 0 and 0, 1 all look different to 1, 1. So they all look like, at least to me, they're facing left, and 1, 1 looks like it's facing right. There is also an inverter, so you can have proper inversion as well, and well, you've got everything you need to build a computer really, though it would be a bit hard to string it all together. Moving from the abstract to the not quite code, let's have a look at comments. Well, one particular comment, there's a lot of great comments out there, and there's a lot of great comments in the thread linked, but this particular one is of good note because of, how notable it's kind of become and well known. It reads, "Dear maintainer, once you have done trying to optimize this routine and you have realized what a terrible mistake that was, please increment the following counter as a warning to the next guy. Total hours wasted here, 42. So, this is possibly a warning I should put on a lot of stuff that I've made, or maybe a warning that should have been on a lot of stuff I've tried to optimize over the years. Needless to say, I'm sure more hours were wasted there still. Next, let's have a look at something that's not quite a comment, but more the text itself, specifically fonts. fonts aren't that complicated, right? They're just a series of symbols that represent some words. Nothing too complex there, right? Well, yes and no. On the one hand, they are just a series of symbols used for representing different things. But they're actually a lot more complicated than that. Specifically, I'm talking about, in this case, font hinting. Hinting is the process of modifying fonts in different ways to try and make them appear better on different platforms, on different screen sizes, different font sizes, so on. So it takes in all of this data and produces a series of changes to the font that are performed on it so that it displays better, so it doesn't look so crushed or whatever. Very useful. But how do we implement that? Well, at least the answer come to by one font engine, TrueType, was a virtual machine. We'll have a font handling virtual machine that executes code from inside the fonts to determine how to modify the fonts. And this code has full branching, infinite loops, so on. So really, it is capable of doing everything needed to build yourself a Turing machine inside your font. Very exciting. And also a bit of a reminder that you should be careful what fonts you install, maybe. Anyway, next we'll enter one of the bigger chunks of this talk. We'll have a look at the C zone. So this is the zone to do with the programming language C, not cursed, though the C could stand for that. Who knows? Let's start with something quite integral. We'll start with nasal demons, or specifically, why do programming languages need to behave well? Do they need to be well defined? And the instant answer is probably yes. But actually they're more like this quote from the Hitchhiker's Guide to the Galaxy. They need rigidly defined areas of doubt and uncertainty. It's not that they need to be well defined, it's just that you need to know where they're not well defined, so you can avoid those bits. Or not, as the case may be. So let's introduce undefined behavior, which you probably have come across before if you've looked at this level of stuff, but you might not have. Undefined behavior is executing something whose behavior is prescribed to be unpredictable. So where the spec says something will happen, who knows? Some good examples of this in C are, for instance, attempting to modify a string literal. Now, what's so strange about attempting to modify a string? Well, if it's a string literal, you don't know where that string's actually located. Is it in read-only memory? Is it in your program's memory? Where is it? And you don't know where that is, so it's undefined behavior to do so. Really, you should copy it to somewhere first and then work with it. Integer division by zero is another good example of this. But that's more a maths thing. It's pretty undefined in general. And there's lots more cases of this. So why am I referring to it as nasal demons? Well, it all goes back to an old post that, to hammer home the point, said, when the compiler encounters a given undefined construct, it is legal for it to make demons fly out of your nose, i.e. something random and unpredictable will happen. And from then on, it's become a synonym for undefined behavior, though probably for brevity most of the time you'll just see UB. So let's have a look at how we might actually use some of those nasal demons. Specifically, let's have a look at a very classic bit of code, the fast inverse square root used in Quake 3. So, as you may see from this source code, it looks a bit strange. Specifically, there's some weird things going on with pointers, and there's some comments which are disheartening to say the least. Specifically, evil floating point bit level hacking, and what the fuck, which are always good comments to have, I think. So let's actually have a look at what it does. It takes the number to square root and interprets it as a long, not as a float, as it actually is, aka the evil bit level hacking. Then it shifts it by 1 to the right. Then it subtracts it from a magic number, which is important but is too complicated to explain here. aka the line, "What the fuck?" And then it converts it back to a float. It then improves the approximation it's produced by doing this, by doing 1, or originally 2 it seems, based upon the commented out code, iterations of Newton's method, and then it's done. And all of this produces a result that is 4 times faster than the common method using lookup tables done at the time. It does make use of undefined behavior, specifically converting a floating point number to an integer, as is done here, by just simply moving the bits and making them treated, well, not even moving them, just treating them differently, is undefined behavior because you don't know how the floating point number is implemented under the hood. In this case, they're assuming it's a particular form of IEEE implementation to perform this bit-level hacking they're doing. However, while it was 4 times faster, it wasn't really useful for long, because in the same year as the game was released, there was also a new instruction added to the SSE extensions for x86 CPUs, which could do the same thing but faster again, and without hacks. So next we'll have a look at something quite closely related to GoTo. Now, people have probably heard that GoTo is considered harmful, which is a joke in its own, well, I don't know about a joke, is a meme in its own right. But there are things even stranger than GoTo. And I'm not talking about come from as well. I'm talking about the non-local jumps that exist in C, specifically set jump and long jump. So, what do they do? How are they used? Are they used? Well, they are used, and they do something that's actually quite useful. Specifically, they allow you to take a jump buffer, as it's called, and then use set jump to fill that at a particular point, and later use long jump to use that to jump back to somewhere else. Where else? Anywhere else, really. It can jump backwards, it can jump forwards, it can jump all around the stack. And depending on implementation, it might even not overwrite bits of it, it might not even override bits of it. You might be able to do crazy things like jump backwards and forwards using set jump and long jump, which is beyond the C99 spec, but is implemented that way in a lot of ways, because it allows you to do coroutines. Even if you don't have that, it allows you to do exception handling and stuff like that very efficiently. And possibly more worrying for some people, it's used even in cars, which, let's not get too into that, but let's just say one of the biggest operating systems for cars uses it quite extensively. So yeah, you can jump anywhere you want to from anywhere else, and nothing's stopping you really. Much more powerful than GoTo, and as far as I know, no one's written something about it being considered harmful yet. Next, let's have a look at something which is a bit more obscure. You've probably come across, if you've programmed at the right areas or in the right languages, with the complexities of memory allocation. So it probably won't be any surprise to you that there is some weirdness around them. So if you've done memory allocation, you've come across probably something like malloc, which allocates memory on what's called the heap, and you may have come across, well, no, you've definitely allocated something on the stack, e.g. a variable or something like that. But did you know that you can allocate stuff on the stack in the same way you'd allocate it on the heap? Specifically, there is a malloc type thing for the stack, alloc A, that allocs a memory, so gives you some memory that's just on the stack instead of on the heap. So when you leave the correct context, it gets removed just like anything else on the stack would be. Great, how useful. Except the stack has many more limits on it, and this can be a bit of an issue and cause some weirdness, to say the least. So a good example of this is that if you're going to be automatically allocating stuff on the stack, then maybe you want to know when you've reached the limits of the stack, because there are some limitations there. Well, alloc A doesn't have you covered there. you won't get an error message when you run out of memory and it can't expand the stack frame anymore. Sorry. You also can't use it in specific places. For instance, on some platforms, if you were to use it in a function call, then it would end up allocating memory on the stack in the middle of function parameters as they were being populated onto the stack. So, also not a good idea. So, as you can imagine, it's not so used. But the concept of allocating things dynamically on the stack like that is basically used by tons of other languages. It's just probably not a good idea to use LK unless you know what you're doing. Then again, that's the same for all low-level memory management. So, I'm sure there's something, even if some of these things maybe they're cursed, maybe they're not. I'm sure we can all agree printers are pretty cursed, just in general. But sometimes it's not always the printer's fault. For instance, you come across an issue, maybe you're trying to print a document and you're trying to print it from OpenOffice. You printed lots of documents, work perfectly fine. Then you print this document and it fails to print. You get an error. How strange. You try and print it the next day, it works. And then you discover that actually it's not this document, it's any document on a Tuesday. Interesting. So what's to blame here? Is it the printer? Is it the drivers for the printer? Well, no. In this case, it's a number of things. Specifically, it's the file command, but being used by OpenOffice. So it's using that command to try and identify the file type of the file it's trying to print, which is a PostScript file that's just been generated. So what's the problem? Well, the PostScript file that's just been generated has a header, and in that header is a date. And that date contains the date on which it was generated, i.e. the current day. Well, that wouldn't be a problem, and everything works fine, except for the fact that there is a rule that overrides the PostScript rule to identify PostScript files that says if starting at the 4th byte there is the string exactly tu, i.e. the start of Tuesday, then it is in fact an Erlang related file. Which in this case means that if you're printing on a Tuesday, you're printing an Erlang file instead of a PostScript file, and nothing wants to do that. So, printers, not always at fault, but moving from printers, not necessarily at their fault, to something more cursed about printers. Specifically, if you've used printing on Unix or Unix-like systems, you may rarely come across an interesting error, a slightly worrying error. Specifically the error, LP0 is on fire, or LP0 on fire. LP here is short for line printer, 0 being the first one. Hopefully your printer isn't actually on fire, and it probably isn't. This error message theoretically dates back to the 1950s and 60s, when printing was just getting started, and, well, computerized printing was just getting started, and it was still somewhat unreliable in a lot of ways. So, this is specifically about the minor chance that maybe something might be on fire. Rarely, because it's probably not a good idea if it is to feed more paper into it. But this is still around in software, and it actually really means that there's some kind of error. Why on fire? Well, it was to encourage the whoever was trying to print to go check the printer as fast as possible, just in case it was. It is, in many ways, just a throwback to the past, but is still present in modern Linux. You can still go find the on fire error message, which, you know, would be very worrying to get nowadays, and hopefully never happens to me, lest my printer really is on fire. Speaking of fires and computers, let's talk about Halt and Catch Fire. Specifically, not the TV show of the name, but the kind of fictional instruction Halt and Catch Fire, or HCF. What is it? What are we talking about here? So the idea behind it is it's basically a generic term for an instruction that causes a specific behavior. That is, it causes the CPU to halt unrecoverably and possibly causes it to do something else along the way, which maybe apocryphally causes things to heat up and catch fire. We don't know it's ever happened, but that's where the root comes from. This is actually quite a common thing, particularly in a lot of older CPUs. In the Motorola 6800 CPU, for instance, there was an undefined instruction which caused the CPU to seemingly halt, but just get stuck reading all the memory forever. So, i.e. acting as a 16-bit counter, effectively going from 0 to 2 to the 16 minus 1 repeatedly on the address bus. While this wasn't particularly useful to the end user, it was very useful in hardware debugging and may have been something added for that. In the Intel 802.86, there was a real halt instruction, HLT, but there was also an undocumented opcode that caused the CPU to halt unrecoverably until reset, hence theoretically some kind of HCF instruction. And in the MOS 6502, there were in fact as many as 12 different invalid instructions which would cause the CPU to go into an unrecoverable halt state. And similarly in the Zilog Z80 derivative, which was used, but made by Sharp, which was used in the Game Boy, there were as many as 11 different instructions, which again would cause the CPU to unrecoverably halt. So, hardware is definitely pretty fallible, but getting stuck where it is probably better than doing something worse. So let's talk about pokes of death, or killer pokes. Now, poke here is specifically referring to the basic command to poke a bit of memory, i.e. set a particular value somewhere in memory. So the poke of death is specifically referring to poking somewhere in memory to cause something to die, usually mean the hardware. So yes, hardware isn't even safe from that pesky software. It can cause irrevocable damage. So, an example of this was on the Commodore PET. On early PETs it was discovered that there was an I/O register, which if you set it using poke, if you poked it, then you could cause text to display faster with some minor added glitching, effectively just unlocking some speed stuff to make things less synchronized but faster rendering, which was great. Higher speed updating of text, etc. was really useful, except in some newer PETs that came along the video system was different, and doing this would cause more extreme glitching and theoretically cause permanent damage to the CRT, so not so good. Also, another example was on the TRS-80 Model 3, which allowed switching between 32 and 64 column text modes. This was accomplished, however, using a relay, i.e. an actual electromechanical component, which was in the video system. So every time you switched, the relay would turn on and off. So if you were to, say, write something to do this repeatedly, then you could theoretically wear out and break the video system. And that's just a few examples. The list goes on, just like in the halt and catch fire examples. So let's move on to something that's theoretically much more integral to processors, but is very difficult. Let's specifically look at division. So, dividing numbers on computers is hard, which you probably already know, but in case you didn't, it is. It's not quite, doesn't have to be as hard as repeatedly subtracting, but it is similarly difficult a lot of the time. So, Intel decided that for the Pentium series of processors, they wanted to speed this process up. Specifically, they wanted to get rid of the old system and bring in a new system which was much faster, but did use a series of lookup tables to help it out, which was fine and good, except for the fact that when they were producing these, they misdownloaded 5 of the values that were in these massive lookup tables, just 5, into the machine that did the etching of the hardware. So the hardware was etched with these mistakes in. That must be a tiny area, you say. Well, yes, it was, except the algorithm used was recursive, which meant that this error compounded on itself, and in particularly bad cases, could actually get up to the fourth significant digit, which is not great. In fact, it's more than not great, it's a big issue. And theoretically caused issues in lots of different places, though some of these are pretty anecdotal. One of them was supposedly in the source engine. There was an issue with a door closing correctly somewhere to do with it. Anyway, like I said, in the worst cases of the fourth significant digit, and this was significant enough that the CPUs had millions of recalls. But it did have a more positive side effect for the world of CPUs in general, and like a lot of these cursed things, did kick off more positive things. Specifically, in this case, we're talking about formal verification of bits of CPUs, specifically floating point operations in this case, but just in general, formal verification is probably a good idea about these kind of things. So we'll leave off looking at something that is very common knowledge probably, but that is right at the bottom of the iceberg as it is rather foundational, which is the first bug was a bug, which most people probably know, but in case you didn't, it was a bug. Specifically, it was a bug that got caught in some of the machinery in a Harvard computer from the 1940s. Or at least this is the common accepted story. Who knows if it's actually true at this point, but that is theoretically where debugging something came from. And I think it's only fair that we end with this because really this is probably part of the source of the curse. We've been cursed since that first bug was destroyed by that computer. Computers are looked on unfavourably by the bug gods, or something similar. Well, I hope that Let me try that one again. Well, I hope that whistle stops. Well, I hope that whistle stops. That turns out to be quite hard to say. Well, I hope that whistle stop tour has been interesting and told you a few things you didn't know already, though probably quite a few of you have already heard of some of these because I did try and keep it pretty accessible, and I know we do have quite a few people who are pretty interested in cursed things. I'd encourage you to have a look at all of these on the cursed iceberg and just in general cursed things, because they're really most of the time something that's very interesting and tells you something about the underlying system used, which you wouldn't learn any otherwise. A great example is if you were to read the book The Old New Thing by Raymond Chen, named after the blog of the same name, which is about a lot of things to do with the curse side of Windows, but I particularly mean one of the appendices, which I think is available online, and I'll put in the notes, which is all about ways things can go wrong and did go wrong, and some of the moon logic used by developers which caused issues for Microsoft moving into Windows 95. But just in general, reading cursed things, looking at cursed stuff, is a really interesting way to learn stuff away the way computers work in general, or just have a bit of a laugh sometimes. So, I hope that's been interesting. In the meantime, remember that computers really are just cursed sand that's been flattened into a rectangle and had lightning put inside it, so there's bound to be some cursedness in there. And thank you very much for listening. If you're listening live, and watching live in fact, then there will be a Q&A in Discord afterwards, which you can take part in and ask me all sorts of obscure questions I won't know the answers to. Or otherwise, you can join Slack and at me, where I will proceed to probably not know the answers. But yes, thank you very much for listening, and go out there and enjoy your cursed sand.